Swayam Prabha. Digital India. Educated India.
Hello. Yeah. Hello everyone. Welcome back. So in the last lecture, we introduced a qualitative description of optical properties of materials. We talked about metal semiconductors and insulators. So in this lecture, we would like to develop some insight. So we will develop a model which is known as Lorentz model, which is very widely used, and it's something that will help you understand material properties very well. Okay. So the whole idea is that if you look at the optical properties, let's say refractive index, epsilon, or even conductivity, they look like a set of numbers, but there's an underlying physics which actually drives it, and we would like to understand that. The most common way of describing that is by making an approximation that each atom in the material is behaving like an oscillator. Okay, so we know of, let's say, the nucleus, which is attracted to a electron, right? Electron is attracted to a nucleus. So we can think of it in these terms. So we can talk of a spring mass system. So we have two masses of different. This is the mass of the nucleus, let's say Mn, which is heavier, and the electron, which is of a lighter mass, and they are connected by a spring, which in this case represents the Coulombic attraction. Okay. Now this spring mass system is subjected to an electric field. What would you expect in this scenario? Of course, we understand that the electric field will drive the positive charge along its direction. Okay. In this case, since let's say the nucleus is heavy, we can think of that as fixed, and the electron is actually moving relative to the nucleus. Okay. So in this case, what you would see is you will have the nucleus, and then there is spring. As electric field is applied, the spring will stretch and compress, right? That's what you would expect in a regular system. Okay. And then it would compress back, let's say. And the equation that describes this motion is essentially simple harmonic motion, right? So this we have studied in classical physics. So let's say I can write my position as x equal to x naught sine omega t. So about a central position, the position of the electron is oscillating. Okay, and this is a simple harmonic oscillator. Okay, how does this help us? Well, it helps us because this spring mass system has a resonant frequency. Okay, and we have studied that in classical physics. So the resonant frequency omega naught is basically root over k by, I'll call it mu, which is a reduced mass. Okay, because we have two particles, we are just dealing with, we want to deal with a reduced mass so that that's easier to describe. So the reduced mass is mass of nucleus plus 1 over mass of electron, so harmonic mean. Okay. So now what happens? So what if the resonance is present? So to understand that, we have to think of resonance. Resonance is a very general phenomena. It occurs, from electrical circuits to civil engineering buildings and so on. So the idea is that if you have a system, it has a natural frequency. Okay. In this case, that natural frequency is essentially omega naught. Okay. Now, what happens when you drive that system externally with a frequency which is, let's say, lower than resonant frequency or higher than resonant frequency or at resonant frequency? What happens? Okay. For example, if you drive the system at, drive in the sense, I'm applying an electric field of the form E equal to E naught exponential I omega t. Okay, right? That is my driving force. Minus I omega t is, I didn't write the space dependence, but that's what you would understand that. So now what happens if this omega that you're applying from an external electric field is equal to the resonant frequency? Okay, omega equal to omega naught. So what happens? So in this case, I mean, it's our experience that if you are actually at that frequency, you get a very large amplitude of oscillation, right? So this results in strongly amplified oscillations, right? And these oscillations, essentially, how does the energy for the oscillations come about? Well, it comes from the driving frequency. Just because the frequency at which the driving force is operating is the same as the natural frequency, there's this maximum transmission of energy. Okay, so this leads to strong absorption. Okay. Now, what happens if my frequency is lower than the resonant frequency, or it could even be higher than resonant frequency? Okay. So what if omega is greater than omega naught? In this case, I'll just say far away. So, and omega is less than omega naught. What happens? In this case, in both these cases, the incoming source, the light, right, it does not interact strongly with the medium. So what is a medium after all? It's just this collection of these oscillators, right? So it does not interact. The incoming light does not interact with the medium. It does not, I should say, strongly. Okay. So what I mean is, because when the light is incident, the oscillator is not going to respond instantaneously. There's going to be a phase lag, right? Because it's a mass system, it has a small amount of phase lag. So because of this phase lag, as the light is propagating in the medium, it accumulates the phase. The phase gets accumulated over a distance, and then this lag gets accumulated. Okay, so basically, phase lag between E and the X, right, gets accumulated. Okay, and this essentially leads to slowing down of light. Okay, so the light propagation in this medium, let's say velocity, now becomes c by, let's say, n. Essentially telling you how much on an average, what is the phase lag that is accumulated. Different materials will have different amount of phase lags. Let's say if I have silicon dioxide, it will have a certain amount of phase lag, and if you have, let's say, aluminum oxide, sapphire, it's going to have a different amount of phase lag. Okay, this is away from the resonance. Okay, but the amplitude is not going to be very strongly influenced. Okay, think of it like, you know, you all must have experienced a swing, right, that we have in children's playground. So if your driving force in that case is you're pushing the swing, that is a driving force, and there is a certain natural frequency to that, depending on the length of the swing, the rope, and the mass and all that, right? So if you apply at the natural frequency, the maximum amount of amplitude is reached. Whereas as it is moving, if you apply a force out of phase, that means as it is, let's say, you know, it's coming towards you, you push it, then you're actually reducing the amplitude. So you're trying to drive it out of resonance. At resonance, if you drive it, it just continues swinging for a long time. Okay, when you try to apply force out of resonance, then quickly it will dissipate. It will not go on for a long time, right? You all have seen this. So essentially the same model. This simple harmonic motion is a very, very useful model in a lot of areas of physics. Okay, so exactly the same thing is helping us describe this. So now, because of this, what we are saying is the response of material also is dependent on the oscillations. Okay. Now, not just electronic oscillations, oscillators, you can also have vibration oscillators. For example, I can think of a crystal, let's say of sodium chloride, right? We have sodium plus and chlorine minus, right? This is a sodium chloride crystal. Now, when I have such a system, these sodium and chlorine atoms are not fixed. They're going to vibrate. there is some amount of vibrations that happen, and these vibrations are called as phonons. The bonds essentially stretch and compress and out of plane, in plane, and so on, and these movements of the bonds are known as phonons. Okay, the lattice vibrations are known as phonons. So this need not be even just a polar crystal like this. It could even be silicon, where you have covalent bonds, right? It's a tetrahedral structure. Covalent silicon is bonded to 4 different atoms. But then even in that case, you will have oscillation, the phonons, the lattice vibrations, which will lead to absorption. Okay. So now, what is the resonant frequency of these oscillations? Okay. So we saw from our simple oscillator model that omega naught is equal to root of k by mu. Now, in the previous case, we had one electron in the nucleus. Okay, the effective mass is going to be small. But in this case, let's say of sodium chloride crystal, you have 2 larger atoms, sodium and chlorine, because of which the reduced mass mu, right, is going to be larger. If you put in the numbers, you will see that immediately. So now, if this is larger, mu is large. What does it mean? It implies that your omega naught of, let's say, ions, if I'm talking of ions or rather vibrations, right? Omega naught of phonons, let's say. Phonons is going to be less than omega naught of electrons. And these both can be present in this material. It's not exclusive, right? You have definitely bonds of electrons being held by atoms. That is there in all material. In addition, you can also have phonons which have a different resonant frequency. So it means that a material need not have one single oscillator, but it can have multiple oscillators, right? And the frequency at which they respond is different. For example, here, the phonons we talked about, these are dominant at IR wavelengths. Dominant at IR wavelengths. For example, I mean, I would say in the sense 3 micron to 10 micron range. Typically, you can also have some longer, even 25 microns up to that you can have. Okay, but these are typically in that range, okay, around 50 to 100 terahertz kind of range, 10 terahertz. Okay, whereas electronic oscillators are dominant at these are dominant at visible or near IR. Okay, hundreds of terahertz. All right. So these are this is another type of oscillator. You might say, I mean, this is even more apparent for us that okay, there is this bond which is stretching, right? That's why the spring mass system. You can also think of another type of an oscillator, that is the rotational oscillator. Okay, I can think of what is a rotational oscillator? Think of a water molecule. Okay, so you have O, H, and H2O, right? So now, if I think of, let's say, my if I'm looking at my fingers and I'm looking at the joint between the fingers as an oxygen atom, I can have one hydrogen in this way. So there's one bond this way, and there is one bond this way. So these are the 2 hydrogens, and then you have the oxygen. Now, the molecule, if it's in a liquid form, it can rotate. It can just keep rotating, and that also is a kind of a resonant response. Okay, so it does if you actually, depending on the molecular weights, you will have a very characteristic resonant frequency of this. Okay, so you can have oscillations, an oscillator of this form, wherein it just like, I mean, you see this all the time in your home also. Like, let's say if you have microwave, you drive the microwave frequency is 2.45 gigahertz. It is specifically chosen so that the water has a resonant absorption at that wavelength, and that's why when you cook food, the water in it gets heated up by the microwave. The water absorbs the energy from the microwave, and then it heats up the food, right? So these rotational oscillators, I mean, it can have other types of oscillators as well. Okay, but if you have a solid, of course, you're not going to have that much rotational response, right? It's very, very, I mean, you just have stretching or kind of a swaying kind of a response. Okay, So this rotational response is going to be dominated microwave frequencies. Microwave frequencies. Okay. So these are the different types of oscillators possible. And last, of course, you can also have a free oscillator, free electron oscillator. Free electron oscillator. Like for example, in a metal, the electron is not bound to any lattice site. Okay. So, I mean, this could be things like metals or doped semiconductors, right? These have a free electron response. Essentially, what we are saying is these electrons are not bound, and so that implies that omega naught equal to 0. There is no spring constant. There is no attractive force. There is no restoring force. Okay, that's why omega naught is 0. So that's how you can describe the metals. Okay, so now the whole idea is that the big picture is that you take a combination of these oscillators and you can describe your system, whatever that is. Okay, so how do we do that in terms of a little bit of mathematics? Well, the first thing we will do is we'll write an equation of motion for an oscillator. Okay, you must have done it in classical physics, but I mean essentially you have a system, spring mass, you're going to drive it with a certain force. So you have to write basically the applied force is equal to the whatever forces are there in the system, right? So what is the, let's say you can take the nucleus to be fixed and take only the position of the electron as a variable. Okay, so what we can say is let's first because of there is some force associated with the movement of some of the applied force is going to be applied to move the electron, right? So what happens is mass of the electron, let's say I'll call it m naught, and the acceleration of the electron, right, is captured by d square x by dt square. This is the acceleration of the electron. Okay, that is one thing. Some of the applied force is going to be used up in as damping. The electron gets damped. So because of that, some of the energy is lost in that. So the damping force can be written as m naught gamma dx by dt. This is the damping term, where damping coefficient is gamma. Okay, and then you have a restoring force as well, which is basically kx. The kx I can write it as okay. So I know that omega naught is root over k by m. So k I'll write it as m omega naught square. Okay, so the restoring force is k into x, right? So I can write this as m naught omega naught square x. Okay, all of these are actually forces experienced by the electron, restoring force, and all of this is going to be equal to the applied force, which is simply the electric field. Charge times electric field gives you the force. Okay, so this is equal to minus charge E. Okay, so this is the driving force on the right side. This is simple from arguments of classical mechanics, that you are applying a force that has to be distributed into various components. That's it. Nothing really significant in this. Now, what is the solution to this system? Okay, you might have seen it in different contexts. The way to find a solution is first to ask what is the driving force. Okay, the driving force is electric field, right? I have an electric field which is going as E of t. It's a time dependent electric field, so I'll write it as exponential E naught exponential minus I omega t. This is a function of time. Now, if I have such an electric field, what will be the solution of this equation? What do I mean by solution of equation? Well, the basic question we are solving the equation means what is x? If you know x, so what is the x that will satisfy the equation that is given to you? Now, equation of motion, right? So, well, the usual way of doing it, the standard approach, is to guess an x. And what kind of a guess would you make for an x? So I'll say x is equal to x naught exponential minus I omega t. Okay, there's nothing that really I mean, because it's the same form, we expect that it will work. Okay, this is a guess only. Okay, and we have seen it work in many cases, so we know that it will work. Okay, so now if you make this sort of a guess, excuse me, now, okay, how do you solve this? So essentially you have two equations here. Let's say this is equation 1 and this is my equation 2. Substitute 2 in 1. Okay, sub 2 in 1. So essentially you have d square x by dt square. So second derivative of x, that will give me there will be I, so I square, so minus m naught omega square x. Okay, I mean x naught and everything is there, so I'll finally strike out the exponential dependencies, so I'll simply write it as x naught. Okay, plus I'm dropping the exponential dependence. Okay, so and then dx by dt. What is dx by dt? Well, it's just 1 ix, right? So I m naught gamma omega times x naught. Okay, and then the last term will be m naught omega square x naught. M naught omega naught square x naught, and that is equal to minus e naught. Okay, so we have essentially dropped out the x dependencies. So, and if you write this, so you can quickly find out that x naught, you can write out an expression for that. It's going to be dependent on, there is the right hand side minus e naught, we'll leave it like that. And now let's collect out the terms. So there's also an m naught. I would like to take that as well on the numerator. And so now this is minus omega square minus I gamma plus omega naught square. Okay, so this is going to be omega naught square minus omega square minus I gamma omega. Okay, this is going to be my solution, right? X naught. So quickly, if this is x naught, let me move this a little bit here. If this is my x naught, x of t is going to be this x naught times exponential minus I omega t. This is my solution. So to understand resonant response, what is going to be my x when omega equal to omega naught? So the question is, if omega equal to omega naught, what is x of t? Okay, so what you're seeing is, you can actually separate this out into real and imaginary parts, and you will see that if you are at resonant frequency, the amplitude blows up. Okay, the denominator essentially becomes close to 0, and because of that, you get a very large amplitude. Whereas if you are away from the omega naught, the frequency is slightly left or right, then immediately the denominator is large, and then because of that, the whole amplitude is reduced. Okay, you don't have a very strong response. So this essentially is the resonant response that I was talking about, right? So if it's x naught, x of t exhibits large values. Okay. If omega is not equal to omega naught, and it's a little bit away from it, okay, let's say it's not very close to omega naught, okay, not close, okay, what happens? Well, x of t is not large. Okay, in fact, I should actually take a phase term, and we have to be a little bit more exact, but I think for the purposes of this discussion, I think it's enough to actually forget about the phase part right now. Okay, all right, you have this solution. Okay, so what if I have a position? I know where the electron is, but does it serve anything for us? Okay, we have to relate it to the epsilon. That's what finally we are trying to do, right? We are trying to derive a model for how an electron moves in a solid. Okay, how do we relate it to the microscopic properties? Okay, the way we do that is, if you look at a system, we can define polarization, which is essentially the macroscopic response. Overall, let's say if you're applying electric field in a medium, what is it doing? It's going to polarize the material, right? We talked about it when you introduced dielectrics. So it's going to introduce this polarization to the dielectric, right? So that is the macroscopic response. We don't really need to consider what happens to each individual electron. The material as a whole, we say it is homogeneous because the distribution of the density of the material is same everywhere. Let's say if I take glass, the density of atoms is same everywhere, or rather molecule SiO2 is same everywhere. So it is averaged out, and overall you have a polarization that occurs. Okay, and that polarization is simply, by definition, it is dipole moment per unit volume. Okay, this is my polarization. What is dipole moment per unit volume? Or the dipole moment is simply going to be, let's say there's a density of atoms, okay, n. Okay, so let me say I have n, which is the density of atoms, and then times the dipole moment will give me dipole moment per unit volume. Dipole moment is simply charge times a distance, right? So this is going to be simply n. If I'm talking of electrons, I'm going to use a negative charge, so minus Ne x of t. So what we have, the oscillator is essentially a dipole. And what is the dipole strength? The strength is proportional to the displacement, right? Dipole moment is charge times the distance. So do we have any questions here? Yes.
I have one question.
Sure.
In the beginning, we derived the equation of motion.
Mm-hmm.
So considering a single particle.
Mm-hmm.
But now we are, when we are talking about polarization, we are applying that the displacement to all the particles.
Mm-hmm.
We are assuming that all the particles move the same. Am I correct, sir?
Yes. Okay. The question was, let's say when we derived this equation of, we wrote this equation of motion, we said, okay, one single oscillator, spring mass system, we considered and we wrote it, right? Then now when we talk of polarization, we are talking of the material itself. Okay. How is that justified? The reason it is justified is, if you are thinking of this oscillator as simply an atom, right? Where a nucleus is, electron is bound to a nucleus, and there is basically uniform density of material, like let's say glass, right? It's very uniform. So I just look at the density of atoms and then times the number of dipoles, the dipole moment. One single dipole moment I'm taking, and I'm simply taking the density. So that will give me the total dipole moment in that volume, right? Per centimeter cube. That's what we need. Okay. So n is a per centimeter cube that's coming in the volume term, because we know how many dipoles are there. So if you have one dipole in 1 centimeter cube, that's the dipole moment per unit volume. But let's say there are two atoms. Each atom is contributing, let's say one, then it will be like 2 into dipole moment per each individual dipole, right? So that way it is density times the dipoles. Okay. So so now we are able to do that. So any other questions? Okay. All right. So if we do this, now we know what is x of t from our previous expression, right? So this is simply going to be x of t has an electric field term here. Sorry, there's a negative term here in the x of t minus E, right? And there's a minus here, so I'll simply remove that, and I'll say my n into p, that the polarization is simply going to be n E, and E by m divided by omega naught square minus omega square minus I gamma omega. Okay. So this is my polarization. Okay. So essentially what this is telling you is, if you are at that resonant frequency, you have a very strong response. If not, the response is not strong. Okay. So this is how my polarization responds. So we're one step closer. If you remember from the first week, we said electric displacement D, right? D is simply epsilon naught electric field plus polarization. Okay. And that we wrote it as epsilon naught, epsilon relative times electric field. This is what we did. The only thing that we need to note here is that, this polarization, it can have two components to it. You have a background component. Okay. So background polarization, P background I'll say. And then there is a resonant polarization, resonant term. When I say the background, essentially if you have material, we are saying, we used to say that epsilon naught chi times E. That's my background response, right? Even if there is no resonance, it's going to be there, okay? In addition, you're going to have a resonant term which is simply going to be Ne square by M. Okay, epsilon naught, okay, so I won't take that. 1 by omega naught square minus omega square minus I gamma omega. Okay. So I can have this, right? So if I combine these two, I can write an expression for the relative permittivity. Okay, epsilon R. My epsilon R of omega is going to be frequency dependence to this, and this is going to be simply the background term 1 plus chi plus the resonant term, but because we are taking out an epsilon naught, so this is going to be Ne square by M epsilon naught into 1 by omega naught square minus omega square minus I gamma omega. Okay. So this is the response, okay, and we usually write it in a slightly different form. We say that this quantity Ne square by M epsilon naught we define as a plasma frequency, okay. Omega P I'll define as Ne square by M epsilon naught. Well, it's going to be square root of this, okay. So because of that, epsilon R of omega is going to be 1 plus chi plus omega P square divided by omega naught square minus omega square minus I gamma omega. Just make sure that dimensionality is satisfied, okay. We are talking about square, so wherever I have omega, it should be square. 1 second. Yeah. And when I have gamma, I'm taking a product of gamma and omega. The overall thing is frequency square. Okay. So this is the response of my material.